Uh, in this video, I'll be trying to prove the Euler-Lagrange equation, which states that the partial derivative of f with respect to y minus the derivative with respect to x of partial derivative of f with respect to y dot is equals to 0. So, in order to prove that, I have taken the basic problem of calculus of variations to determine the function y of x such that this integral this integral would be an extremum. In this particular case, I have supposed it to be minimum. So here function f, uh, it's a function of three variables x, y and y dot, and y itself would be a function of x. So as a whole, this function f would be a function of x only a variable x. Therefore the limits is from x1 to x2. So let's suppose the point x1 is here and x2 is here. Then this would be our minimum function y of x. Then let's say any deviation from that minimum function would be given as eta x. And in order to give the different deviated function from minimum function, I have denoted them with, I have multiplied the deviation function with scalar to make it different. So the deviated function or the neighboring function can be written as y of alpha and x equals to y of x plus alpha times eta of x. All these deviated function also pass through the endpoints. So at endpoints, this neighboring function should satisfy our minimum function. So eta of x1 equals to eta of x2 equals to 0 at the limiting points. Okay, the function, this would become function of alpha from x1 to x2, and instead of y of x, now it would be y alpha x, y dot alpha x. So now if I take the derivative of this partial derivative of j with respect to alpha, then it would be partial derivative of f with respect to alpha plus partial derivative of f with respect to alpha dx. But now I have applied the chain rule so that I could get y and y dot here. From that, we can get the value of dy by d alpha and dy dot by d alpha from the neighboring function that I stated earlier. So the partial derivative of y with respect to alpha would be simply eta of x, and partial derivative of y dot with respect to alpha would be eta prime. So that's what I have written over here. Now if I substitute the value of partial derivative of y with respect to x and partial derivative of y dot with respect to partial derivative of y with respect to alpha and partial derivative of y dot with respect to alpha as eta of x and eta dot of x, then this equation would become partial derivative of f with respect to y times eta plus partial derivative of f with respect to y dot times eta dot, and which is integrated with respect to x from x1 to x2. Now for the second term over here, this one, I have used the integration by parts, and which would give me the partial derivative of f with respect to y dot integration with limiting value from x1 to x2 of eta dot dx minus partial derivative of d over dx of partial derivative of f with respect to y dot times eta x dx with limits x1 to x2. Now since at x1 and x2 at endpoints eta of x would be 0, so this term automatically goes to 0 and only this term remains. So now what I can do is I can substitute this with this. That's what I have done over here. So the partial derivative of j with respect to alpha would become this expression over here. For the extremum value, if I take this eta of x common, and I could say only df by partial derivative of f with respect to y minus d by dx of partial derivative of f dy dot would remain inside, and for such extremum value the dj by d alpha would be 0, since it's either minimum or maximum in which the first derivative would be 0. So I could say this inside expression, when this eta of x is taken as which is factored out, the inside expression would be equal to 0. So that is what I have written over here. So the expression would finally would be partial derivative of f with respect to y minus d by dx of partial derivative of f with respect to y dot would be 0, and that is also our Euler-Lagrange equation, and it's proved. That's it. Alright.